Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is joint work with folks in Redmond. Although to be honest, a lot of this work also happened at Yahoo before I joined Microsoft, but that allowed me to reproduce results onto production data sets, which is kind of convenient. Okay, so the premise of today's talk is going to be all about interaction logging and interaction modeling. Now, what do I mean by interaction logging here? By interaction logging, I mean detecting exactly how users interact with or engage with some interface. Now, I'm going to be relatively abstract here because I want to sort of suggest that these techniques are general. So when we're talking about user engagement here, I'm talking about not just clicks, but also things like dwell time, clicking on the back button. You could think about touch interfaces, or in this talk we'll be discussing mouse movement. And when I'm talking about interfaces, I mean anything the user might interact with. So this would include things like the search results page. It would include things like portal pages or mail pages or Office documents. Now, interaction modeling has to do with being able to predict user engagement on some arrangement of items on a page or some interface that perhaps I have never seen before. Okay, so it's exactly the same definitions of engagement and of interfaces I listed before. So I'm interested in being able to predict how users are going to click. I'm interested in understanding how they're moving the mouse or touching the interface without actually ever having presented this interface to real users. So what's the value here? So obviously for interaction logging, I guess most of us in the room should understand that logging is very important for evaluation of systems. So the richer our logging, the more accurate our logging, the better we can evaluate an interface that we have actually launched into production. Furthermore, beyond this evaluation, we can in an automatic system roll this in as a feedback signal or as some sort of feature that can then lead to better system performance in an automated way. So you could imagine if our metric is computable automatically, it being fed back into some sort of learning system which would then adapt as it observes more and more feedback. Now, interaction modeling, what is the value here? The value with interaction modeling has to do with what I'm calling the pre-presentation phase. So what value does the model have before I've ever actually presented this interface to any users? So for one, it gives me an automated system performance prediction capabilities. Okay, so if I know that there's some relationship between the user's interactions and system performance, then being able to predict users' interaction given a certain presentation or interface, I can then make predictions about how well that decision is going to actually perform. Relatedly, you can use this performance prediction signal as a feature for your ranking algorithm or your arrangement algorithm. So if I have an automated page layout algorithm, the predicted performance of that layout maybe should influence my decision whether or not to actually execute on that interface. And finally, a little bit different, this is a little bit different style of use of this data. We could use these predictive models as a design tool. So imagine that I could, given an arbitrary interface designed by some designer, tell you where the users are going to look, how they're going to interact with that page. That's going to be very valuable for a designer because a lot of times they don't observe that sort of information until they've run a laboratory study or launched a thing in production. So giving the designer the ability to anticipate how users are going to react to pages or interfaces allows them to iterate much more quickly with the design part. So like I said before, today's presentation will be focusing on the mouse as the type of interaction we're interested in, and search results as the specific interface we're interested in. Some of these techniques should be generalizable to the other interactions, and certainly to a lot of these web-based interfaces. Okay, so since I'm going to be talking about mouse, let me try to motivate mouse tracking a little bit. So here are a couple of heat maps of this is eye fixate, or this is eye visual attention, so gaze on a search results page. On the left, we have a search results page which does not include the task pane or entity pane, and on the right, we have a search results page which includes the task pane or entity pane. And what the heat map is what the heat map is giving us is some idea of where users are looking on the page, and it's telling us also that users tend to be attracted to the task pane when it's actually presented on the page. So this is nice. A designer would be very interested in this sort of real data if they were designing the search results page to include the task pane. Now, what does that have to do with mouse? Well, there are also a lot of results. This is a recent result, but other results dating back, I guess, early 2000s, that have found a very strong correlation between eye position and mouse position on the page. So those of us who know about JavaScript know that mouse is pretty easy to track on an HTML page if we encode the right JavaScript. So what this allows us to do is get some surrogate for visual attention on the page, given a really crude sensor, so the mouse. So if we can capture the mouse, we can get some idea of where the users are looking on the page. The figure here is presenting the same task pane and without a task pane interfaces with the eye tracking trajectories as well as the mouse fixation. So the green, I believe, is the eye tracking, and the blue is the mouse fixations. And what they find is that, yeah, they're not perfectly correlated, but there is, in general, a tendency for the mouse and eye to be attracted to the same parts of the page. This sort of result has been studied also within Microsoft. So Ryan, Jeff, and Jorg have looked at the correlation between eye and mouse on search results pages, and have found that you can get within about 200 pixels of the true position of the eye given just mouse data. They've also found that this actual correlation is non-stationary with respect to the page render time. So within the first second, I believe there's less correlation, but as the users start to interact with more and more of the page, there's stronger correlation between eye and mouse. Okay, so today's talk, we're going to be discussing search results pages. We're not going to be discussing the exact relationship between the XY position of the eye and the XY position of the mouse. We're more interested in the general regions that the users are looking at. Okay, so here's our SERP. What we're going to do is chop that SERP up into different areas of interest. Okay, so here I've got all the algorithmic results as separate areas of interest. I have the image answer as a separate area of interest, the advertisements, the navigational bar, and the search box, and the left rail. Now, the type of data I'm going to be looking at is, like I said before, this mouse tracking data. So I'm going to be recording where on the page the mouse has been visiting throughout the course of a user session. So user issues a query, I chop up the page into the areas of interest, and I start recording where the mouse is. So how is this implemented? Like I said before, the instrumentation is based on JavaScript. So the JavaScript can actually record the geometry of the different areas of interest. It can also capture the mouse trajectories. And in practice, how that's beaconed up is you're sending up the header information with all the AOI geometry information, which is stationary more or less with respect to the session. And then every time you observe mouse movements, you fill this buffer that you flush out as the buffer gets full. All right. So for the purposes of this presentation, I'll be referring to a page arrangement as a configuration of these modules on a page. Okay, so these modules or items on the page are things like algorithmic results, image answers, advertisements, etc. So one arrangement might be 10 blue links without any advertisements. A second arrangement might be 10 blue links plus 2 advertisements on the right. And so the set of all arrangements are the set of all legal slottings of items on the page. So this is a plot of the distribution for over page arrangements for 2 search engines. The 2 search engines you can probably guess, but the more important thing to notice here is that the relatively long tail of arrangements on this page, or on these search engines, which is to say that a lot of queries observe these weird configurations that we haven't seen before, which just kind of makes sense, right? Because when a query is issued to a search engine, you might have a very different distribution of intent than a query you've seen before. And because a lot of the page layout is automated these days, we're going to see novel configurations of advertisements and answers on a page. So you're going to begin to observe all these really strange configurations that we haven't seen before. That said, we have a lot of things at the head of the arrangement distribution, which are things like 10 blue links or 10 blue links plus advertisements. Okay, so let me move on to the modeling part of this talk. So this is sort of a graphical representation of one of the ways we might think about how users interact with a search results page. So here I've labeled several different modules as M0 through M6. Okay, for the purposes of this graphic, I'm going to say there are 5 search results labeled M1 through M5. M0 might be an advertisement. M5 might be search assist. The unlabeled node at the beginning is just a start state. And the way that people often think about modeling users interacting with the search results page is that they start at the first algorithmic result, so here M1, and then linearly scan down the page, so M1 through M5. The premise of this presentation is that in practice, that's probably not so realistic. What's more realistic is something like this, that the user's not starting at M1. They could start at any of the arbitrary elements on the page. They might start on the advertisement or on position 4. And then they can jump around arbitrarily between the different modules. So you might start at algo result 4, then your visual attention might jump up to image which is slotted at 0, and then jump around. Okay, so that's the premise of the model we're going to be proposing. Let's see if the data actually gives us some intuition about where we're going. So like I said before, the classic model assumes the linear traversal of the ranked list. So this is a visualization I'm going to be using for the next few slides, and so I think it's worth explaining a little bit. So this is a square matrix where each index of the matrix represents one of the modules on the page. So here I have N, which is the navigational bar at the top of the page, which allows you to select a vertical. I then have the 10 algo results. And then I believe S is search assist. R is related queries. H is historic queries. And then advertisements is A. So the way to read this is that for a given row, so let's say from position 1, the entry is proportionally white according to the probability of going to that column. So in this case, the probability for the classic model, because it's linear, the probability of going from 1 to 2 is biggest, and it's 1, and 0 everywhere else, so everything else is black, and so forth down the rank list. There's no, yes?
What do you mean by search assist?
Search assist, so this is, I believe, from Yahoo data. So I think it was something like query reformulations, that sort of thing. Okay. So yeah, there were at least in this in this data set, there were 3 ways that you could suggest queries. One is recommended queries, one's search assist, and one is these historic queries. Okay? Advertisements.
Which one?
Oh, so these would be, I believe in this example, it was right rail. So it's advertisements on the right. Yeah, it will be because look at the next slide. So here's reality. So this is the actual probabilities based on the mouse tracking data. So what do we notice here? We notice that the transitions are going not just linearly down the page. They're jumping over entries on the page. They're going back up the page. They're going over to the right rail and transitioning down the right rail. They're going up to the nav bar, etc. So the actual reality about what's going on with the users is a little bit more complicated than is suggested in the by the linear model. Now, yes?
How do you jump over a search result with a mouse?
Right, so it has to do with the fidelity of the sampling. So it's almost like we're capturing something like fixations just because the mouse is moving so fast. Okay? All right. So right, in general, it is linearly down the page, but you just do have some complex interactions going on here. So that means that the linear model perhaps should be tweaked a little bit, but it gets more interesting when we start to look at pages that include instant answers. Okay, so here on the left, this is only for the first 6 positions, but I have on the left I have the 6 blue links. Okay, and on the right I have one weather result at position 1, followed by 5 blue links. Okay, so it's a little bit hard to see on this plot. So what I'm going to do is I'm going to essentially divide element-wise the matrices here. Okay, and the next slide is going to present 2 matrices. One where the probability of transitioning is higher on the weather presentation, and one where it's higher on the non-weather presentation. So here's the result of that division. So on the left-hand side, I have the cases where weather it has higher probability of transition than the non-weather result. So one thing we notice here is that there's a higher probability of transitioning up the page towards the first position. And over here, where we have the presentation where the probabilities are higher in the non-weather versus the weather case, we notice that we're actually getting all this probability mass from the transitions down the page. So the mouse, at least, tends to be attracted to this position 1. This is kind of interesting because weather, at least at the time of these experiments, was something that was not clickable. So this gives us some feedback signal for the actual weather answer. Now, if I present exactly the same thing for the image answer, we get similar results. So here I have image at position 4. And this on the left is the case where the probability of transition for the image arrangement is larger than for the non-image arrangement. And what we notice here is that the transition to image from almost all positions, or actually from all positions, is higher than in the non-image case. So the mouse tends to be attracted to the image. And over here, where we're trying to find out where that probability is coming from, we notice that it's being removed from the positions below image actually going above image. So the things are no longer going from position 6 up to position 1, they're stopping at position 4. Okay, so the image vertical tends to act as a sink in this case. Okay, so that's sort of a high-level description of the data. Now I want to talk about some experiments that we were running in order to try to model what's going on. So the problem definition we're going to be looking at is sequential modeling. So we assume that we observe in the mouse tracking data a sequence of modules that the user has moused over. Okay, so it might be in a linear scan case, algo 1, algo 2, algo 3, etc. Or we might observe a user starting at image at 4 and then going up to algo at 3 and then jumping down to algo at 5. So this sequence of modules is going to be the data that I'm interested in predicting. Now, the actual way I'm going to be studying this data is to try to estimate that matrix we saw earlier. So that black and white matrix, I want to try to estimate the size of those white squares. I want to estimate the transition probabilities between all pairs of modules on the page. Okay? So before I discuss the actual model and how we do that and all the features, in the course of writing this paper, I came across some really interesting related work having to do with shopping. Okay? So that's some scientists in the 60s studying grocery stores, which is exactly what Farley and Ring did in 1966. So in their case, just to relate it to what we're looking at, the set of arrangements they're looking at is arrangements of aisles in a grocery store. Okay, so what are the different configurations of aisles I can look at in a grocery store? What they call a consumer is a person interested or not in buying products. So it's somebody who's navigating this grocery store. And the paths in this case are shopping paths. So how did the person navigate the grocery store? So this is what their data look like. This is data from 2005 when they used RFID tags. They have a grocery store as your layout, and then the paths were the paths that the shoppers took through the grocery store until I think they finally exited. So it starts and then goes all around and comes back. In practice, what they do is they don't look at the actual XY position of the user or the consumer. They're looking at the regions in the relevant regions in the grocery store. So each of these regions is a collection of related products. So this is similar to our areas of interest. In this case, they're looking at things like cereal or produce, etc. And then they're interested in also modeling or measuring the transitions between all these regions. So what is the flow of the traffic in a grocery store given a certain arrangement of aisles and things in those aisles? Farley and Ring in '66 proposed something that looks exactly like what I was proposing earlier, which is a transition matrix between all areas in the grocery store. Okay, so it's always nice to find something like this in a paper from 1966 because it means maybe you're on the right track. Yeah, so they had certain constraints on their model, but more or less it's the same thing, and I'll be returning to it later on too. Okay, so I have this transition matrix. How do I actually estimate those little white squares? Well, if I have a certain arrangement, like 10 blue links and no advertisements, I've certainly observed that in the data a lot. So what I can do is I can get all the data, which here is represented by this matrix D, and count the number of times that I've observed a transition from algo 1 to algo 2, algo 1 to algo 3, etc., and just compute the maximum likelihood estimate of the transition between all pairs of modules. Okay, this is pretty straightforward. The advantages here are that it's easy to estimate. Given a lot of data, you're going to have a pretty reliable estimate. The disadvantages here is that, well, it requires a lot of data to get those reliable estimates. And secondly, more importantly, it's unable to generalize to novel arrangements, right? So if I've only observed 10 blue links with no advertisements, that tells me nothing about the transition probabilities for 10 blue links with 4 advertisements, because the dimensionalities of the matrices are completely different, and it just doesn't make any sense. And introduce the Farley-Ring model. So here are Farley and Ring, a little bit older than when they proposed the model. But they said, okay, so I have this PIJ, which is the transition probability from different parts of the grocery store. What I'm going to do is I'm not just going to count the number of times I've observed that transition. I'm going to featureize the start and the end of the transition. So I'm going to featureize the produce and dairy sections and say, well, given the arrangement of these two things and the identity of these two things, what is the probability of transition? So I'm trying to predict the entries of this matrix P, given the properties of the starting and ending states of the transition. Okay, so they looked at these three features here, which were inspired some by physics, and we're going to look at a few more. So again, the intuition here is we're going to featurize the start and end states and then make predictions based on those features. Here are the features that we're going to look at in the mouse tracking example. So there are what I'm going to call module level features, which are just things like the geometric properties of the module. So what is height, width, area, the DOM class. So is this something labeled as an algorithmic result in the DOM tree? The ID, which also contains some information about what's inside of the object. Notice here that we do not have any sort of image features. So these features are all computed based upon properties of the HTML. This is only done because it's a little bit faster than doing real image analysis. Now we also have these interaction features, which looks at the relationship between the elements on the page. So let's say I'm considering making a prediction on algo 1 and algo 3. Do they have the same DOM ID, the same DOM class? What is the geometric relationship? Is one to the left? Is one on top of the other one? What is the distance and what is the area ratio? So this is an exhaustive list of features. We can always think about more, but these were the ones that kind of made sense at the beginning. Then we have page level features, which again are just properties of the page. So how big is the page? How many results are there on the page? Time of day. And then finally, one that's sort of important, which is the viewport. So what's the thing actually on the page? Right? So the viewport is only going to capture, if the viewport only captures results 1 through 4, transitions down to 10 are very, very unlikely. Now, in order to, the model itself is not super important. We did, because we had a lot of data, we hashed the features, but we also looked at quadratic features, which allows us to look at the relationship between things like, were the relationships between pairs of modules. So if the product, for example, of the two areas of the modules is important, then that would be captured by the quadratic features. Advantages of the Farley ring model are that it allows you to generalize to these new arrangements of items. So if I have trained my model on a bunch of diverse data, I can actually make predictions about arrangements that I have never observed in my data set. So if I've only seen images at positions 1, 3, and 5, I can make claims about what the probability of transition is for images at position 2. Again, it requires a lot and careful use of data when you're training the models, and unfortunately, it's unable to explicitly incorporate the data from the target arrangement. So let's say I'm making predictions about the arrangement of elements that includes images at 2, and I've never observed that. If I begin to make observations, I want some way of incorporating that data. At least in the model as it's defined now, it's not possible, but we can always update the estimates. And the way we do this is we let each row of that transition matrix be a multinomial with the Dirichlet prior, and then we just set the parameters for the Dirichlet according to the predictions from the Farley ring model. Then when we observe target data, we can just update the probabilities in the usual way here. So again, it's Dirichlet prior. So the posterior is just going to be a function of the counts that I've observed in the new data, as well as the predictions from the Farley ring model. So here, okay, and mu here is a hyperparameter, which is proportional to the trust in the Farley ring model. So if you crank up mu, it means you're going to have to observe more data in order to adapt your model. Okay, another tricky thing here is how we use training data for training this model. So what we want to do is select instances so that the model is robust, so that it can actually generalize to brand new arrangements. So one of the things we do not want to do is just sample 10 blue links, because if we sample just 10 blue links, we're never going to observe things. Well, you won't observe images in there, but you also maybe be giving too much weight to things just because they are not diverse enough or they haven't been randomized in the presentation. So we're going to use one of 3 different sampling methods. One is just to use data from the top arrangement. So this would be equivalent to just using 10 blue links. Second approach is just sample K sessions. So here I'm just sampling from that distribution of sessions I saw at the beginning of the presentation. And finally, round robin, which is going to essentially sample without replacement sessions or arrangements, and then a session within an arrangement, overall arrangements, so that I try to get a diverse set of different arrangements into my training set. Experiments. So in the Farley Ring paper, they had 5 arrangements with 5 grocery stores. And it's kind of cool that they looked at the number of aisles. This here, the number of areas is equivalent to our number of modules on the page. And it's actually about the same size. I think in our data set, we have on the order of 20 different things we have on the page. They have all these other properties of their data set, which are fun to look at, including the meat location, bakery location, which unfortunately I don't have on my data set. Now, this is the arrangement where how did they actually get the paths? Well, according to the paper, the model's predictive power was tested with data on actual supermarket traffic flows collected on maps drawn by research assistants who secretly followed shoppers around the supermarkets in Pittsburgh. Yeah, we didn't quite do that, but it's always fun to see how people used to do tracking, and this is, I don't know if you could get away with this these days. At least Microsoft might not be able to. Maybe they would in academia. Okay, so what's our data look like? Like I said back at the beginning of the presentation, we're collecting data from 2 different search engines. They were collected over actually on 2 different times of year. Here's some just high-level statistics. No personal data was used for this experiment, so we didn't look at the query. We didn't look at the user ID or anything. We just looked at the transitions between the between the modules. Certainly, you could think about incorporating those things as you begin to come up with more personalized models about how individuals use the mouse. For evaluation, we looked at 2 different metrics, one of which was the likelihood, the second of which is just the reciprocal rank of the observed target module in your prediction. So this is just sort of like an IR metric, which to replace the probability, just to augment it. They're going to track each other pretty closely, so I don't think it's worth discussing a lot. Okay, so experiment 1. Experiment 1 is sort of a straw man experiment just to make sure everything's working. How well does a model perform on the most frequent arrangement? So this would be equivalent of saying, well, I've trained this model using all sorts of different sampling strategies. How do I actually know how well it performs on the 10 blue links? So the way we operationalize this is we sample M sessions from their most frequent arrangement. So this would be M sessions from 10 blue links, for example, and then evaluate the performance using our 2 metrics. In this case, what we expect actually is it happens is if you train the model using the most frequent arrangements, you're going to perform the best on the test set, which has the most frequent arrangements. This kind of makes sense. Sampling randomly from all of the arrangements obviously gets you not quite as strong performance, but still pretty strong performance because that distribution is pretty skewed. And finally, round robin performs the worst, which again is to be expected because you're investing more in robustness than you are in making predictions about this specific arrangement. Yes.
To understand what you're predicting here, so the reciprocal rank would be there's some kind of target module, and for that one you want to know how likely the user is to transition to that.
Right. So it would be, so let's say I'm at in the data I'm at algo 2, Okay, and then in the data, I've observed algo 3 next. My model is going to make predictions about. It's basically, I mean, the multinomial is going to giving me a ranking over all the other modules on the page. This is the position of that module in that ranking. I mean, they're going to track each other throughout the rest of the presentation. So we can discuss what they are differently later.
Do you allow self-transition?
No self-transition. You could, because, I mean, self-transition is interesting because you could, that's one way you could model the amount of time users have spent on the page or on a specific module, which may or may not be a good evaluation signal. But that's an experiment that we need to do yet. Okay, so that's experiment 1. It sort of confirms that things are more or less working as expected. Now, getting into something we're more interested in, which is how well do the models perform on the least common arrangements? Because this is really what we want. We want to be able to make some predictions about arrangements we've never seen before. So in order to test this, we took the least frequent arrangements of items on a page, and used them as a testing data. So in this case, everything reverses. So of course, if you only train your model using the most frequent arrangement, you're not going to be able to generalize to the least frequent arrangements because maybe you've never observed images in your data set before, in your data set in the top for the most frequent arrangement. Round robin performs the best because it is focusing. You are focusing the evaluation of the model on the robustness. You want it to be able to generalize to brand new arrangements. Random is performing okay, but it's still not as good as round robin because of the fact that you have this skewed distribution. So it's going to be focusing a lot of the modeling effort on the most frequent arrangement. Yes?
Is the absolute value here higher?
Yes, absolute.
You know, as in 0.6, I think I thought so 0.58 on the previous slide, or did I misremember that? Yeah, 0.58. Yeah. So it's actually more accurate on the. So the round robin is more accurate on the least frequent.
Well, are they all? So random is as well. Top is not.
Yeah, but sort of top on top is doing worse than round robin on bottom, because top presumably does have a lot of top. Right? So it's why would that be worse?
So I think it has to do with the number of items on the page affecting, well, the reciprocal, yeah, so it will affect these metrics, right? So if you, so I guess my claim is that, and I think I'm wrong, my claim is that you will have fewer items in experiment 1. So the upper bound on the, I guess, no, the lower bound on reciprocal rank is actually lower, or it's higher, right?
Yeah.
Well, for top, yeah, it doesn't explain. Yeah.
It's worse than bottom.
Yeah. So that doesn't, it actually should be the opposite, if that's true. Yeah.
Could be that there are very specific patterns for specific queries, and that as you get towards the tail, it's also less frequent. I don't know if that makes any sense.
Yeah, I don't know. I think it's worth looking into, but.
Rare is more predictable for some reason.
Yeah.
Because it's rare that you have an image answer and a video answer, but when you have them, it's very obvious that everyone's going to look at one and the other a lot, and
maybe
stuff like that.
Yeah.
Whereas if you just have the array, if you've only trained on the arrangement at the top, you're just going to, you're going to choke.
Right? 10 blue links, people can do all kinds of things depending on what
Yeah, but you would expect it. Yeah, maybe so. Yeah, I think it's worth looking into. Okay, experiment 3. Like I said, we can adapt these Farley ring models. So the way we tested this was to take, I believe, random arrangements, not sessions. Here, random arrangements from the torso of that distribution, and sampled adaptive sessions in order to see how well we improve with performance as a function of the training set size. So here, training size means the number of on-target examples that I get. And And so of course everything gets better with more examples, and everything sort of converges to the same thing. The more important thing to notice, more important thing to ask is, well, at what point do they all converge? Because the point where they all converge is the point where you can actually throw away the model and just start estimating things using the MLE. So the MLE, remember, is just counting number of transitions. So what we observe here is roughly for both metrics, around 150 or 200, they all converge. So what? That just means that the value of the offline model, or the value of the Farley ring model, is that it will let you avoid essentially 200 sessions in a user study. Okay, if we assume that the only way we can get that one way we can get this data is through an eye tracking study or a mouse tracking study, we can actually dodge that cost by running the offline model. So that's one way of quantifying the value of the model. Okay, experiment 4, which is kind of fun, which is to ask a question. Well, this is cool for answering questions about arrangements we've already seen. Now, let's ask ourselves, well, how well can it predict just crazy arrangements? So what do I mean here? This isn't so crazy because things like images look like this. The image results look like this, but it is crazy because what I'm telling the model here is that these are all algo results. So imagine I have 10 or 25 text results arranged in a grid. I want to be able to make a statement about how users are interacting with that page. Okay, so here this is not the diagram, the matrix, the black and white matrix I had before. This is actually each square here is a different result. They're shaded according to the probability of the user looking at that item first. Okay, so the stuff at the top left-hand side of the page is getting more attention than the stuff at the bottom right-hand side of the page. So this is a nice diagnostic exercise to make sure that things are looking right, and we know that we have evidence that users tend to browse top to bottom, left to right. Now let's say I replace one of those things in the middle with an image. So that's an image of the same size as the rest of the text results. The model's predicting that the users will look at the image first and then look at the rest of the text results in the same order it would have before. Let's say we replace 4 of those results with just one big text result. Again, we have in general the same left, right, top, bottom scan path, but the larger element's going to get more attention. And then also when we have one large image, you're getting all the attention on the image, and you're getting a little bit more. You're getting a little attention on here, but certainly not as much attention as if it were all text. So this is certainly not an evaluation, but yes.
Well, it reminds me of Windows 8.1.
Windows 8.1. Yeah. No, absolutely. And I think.
You can do an evaluation. Yeah.
What's that?
You can do it as an evaluation.
Yes, I agree. Working on it. Right. So right. This is not evaluation. This is just sort of a qualitative demonstration of what the model is actually learning. Right. And I think that wraps the presentation. So what do we learn here? That we can learn these robust models to make predictions about what people are mousing over on the page, at least. And if we trust correlation between eye and mouse, it tells us what they're looking at. If we want to quantify the value of these things, the Farley ring model is about the equivalent to 200 lab sessions. And in terms of future work, you can think about the obvious things, which are to extend this to non-SERP pages. So how can we build models about people reading other types of pages, such as documentation pages or mail pages, etc. And finally, since a lot of interfaces are becoming more and more touch-based, we can start to think about generalizing these models to other devices. Okay, so that's it, and I'll take questions. Yes?
So can your model give the optimal order given a set of objects?
I believe that's it's NP complete, because you need to basically you have to go over all different arrangements, and then you also need one thing that I didn't talk about here was which you would need for your metric, is a vector of relevance values, right? So this will output the order a user will look at things. If you essentially do the combination of the relevance values with that, you would get, in sort of in a DCG world, you could get the accumulated gain as they're iterating over this this arrangement. One thing that doesn't capture is the probability of transitioning out of the session as you begin to observe more and more relevant information. So it's definitely something that's one of the reasons I developed this model was for exactly that problem. Because with things like federated search or vertical search, you need a more complicated model than just a cascade model.
So your transition probabilities were row normalized, right?
Yes.
I imagine the column normalized one, especially for grocery stores, is somewhat interesting, right? People tend to buy salsa after buying crisps or something. If I'm changing some layout on my page, I need to know what else I can change to bring people here.
Wait, so that once more. I'm not sure why that's why that would be.
I'm interested in where I'm interested in bringing people to my area of interest. So what else do I need to change on the page to bring people here? Or
Right. I mean, yeah.
Normalized transition probabilities, essentially.
I don't understand how that would be the column normalized version of it.
So yours is from I to J?
Yeah.
I'm interested in knowing from where all people...
Right. So you're right. What you're saying is you want to maximize essentially the sum of the values in the column. Yeah. What are your? I mean, yeah. It's worth asking like what are the degrees of freedom, and I think you have to do something like what Milad was suggesting, which is incorporate the relevance value. So if nothing's relevant on the page, and you're the only relevant thing on there, then the column sum is going to be relatively large. Whereas if the first thing on the page is relevant, even if it's the same arrangement, user might just stop there. So imagine for a navigational query. But yeah, I think it's an interesting problem. But it also suggests that that's an adversarial situation where I'm an advertiser and I want people to look at my thing first, as opposed to letting the algorithm decide based upon what it thinks people should look at first.
Do you think about using sort of graphical interestingness type features just to go beyond blue link to blue link with a badge, blue link with deep links, blue link with...
So some of the right. So some of the DOM level features capture that, because when you say like there's deep links in here, it'll be in the class of that div. So some of that is captured in there.
Sometimes you might show an image next to a search result, which is sort of not an image answer, but it's a web answer with a picture.
But even that is encoded. I mean, the people who work on front end are oftentimes just dropping that stuff in there. So I'm capturing a lot of that. Pardon me?
Essentially, capturing it in the name of the class.
That's right. Which is just cheap. It's not exactly what you want, but it gets you a lot of the way there. What I'm not getting though is, say I have an image answer. I'm not getting any of the analysis of the image itself. What color the image is. Are there faces in the image which will affect the attractiveness of it?
So in terms of the baselines, I was just wondering how much of the gains can be achieved by a simple baseline that only considers the size, or the size of the DOM discounted by the position or something like that. Do you have any results on that?
Yeah, I mean, I think you're right. That's worth looking at. There's a few things to strengthen the baseline, to be honest. Like, one of the things that Philip pointed out earlier is that you're not very likely to see a transition from 3 to 1 without going through 2. So imposing some sort of a planar graph on this thing kind of makes sense. Or doing what you suggest, which is like, don't even worry about data, just look at the relative sizes of things. But then, I mean, so let's say I have the relative size of things. How do I turn that into a probability? It's not clear. Or the orders. I mean, we can sit around and think about ways to hack that out, but I think as it's defined here, it's just like we have this bucket of data here, so let's just pour it into the model as is and let it go.
So, yes, so what I'm trying to find out, I mean, the model is very elegant, but I'm just trying to see how much of the gains could be simply achieved by something very basic, and how much this elegant model is adding on top of simple heuristics.
So the problem with heuristics is that as the types of things you're adding onto the page become more and more complicated, you have to add more and more heuristics. So, for example, now I want to model deep links differently than non-deep links. Well, now I need to come up with a heuristic for how that will turn into a probability. Or let's say there's an image in this algo result. How does that change things? So part of the reason the baseline is sort of simple here is because I didn't want to invest a lot of effort into the baseline when there was a lot of modeling work to do. But I agree with you. If we sat around, we could certainly come up with stronger baselines, but I don't know if it'd be worth implementing.
Kind of related, do you know the relative importance of the features you put into the model?
I think I don't have them here. I think I ran that analysis a long time ago, but I don't remember them off the top of my head.
Is there a reason to restrict this to search results?
No, I mean this is one of the. I mean, that's where the data is now. If we could run these, if we could run the data collection on non-SERP pages, that would be great. I would love to do those experiments. The problem is that, or I mean, the good and bad thing is that search has the most sophisticated login infrastructure that I've seen across properties. So that's probably one of the reasons why that restriction's there. Oh, there's one more question.